Units of measurement, significant figures, and uncertainty. Second lecture. Um, a little bit about chemistry. Whenever we do experiments, it's very similar to cooking. If you make a simple mistake when you're cooking, your food might come out too burnt or not cooked enough. The same thing happens in chemistry. If you don't use the exact measurements, you might not make product. You might make something you probably shouldn't have made. Um, Everything we do in chemistry has to be precise and accurate. Any little mistake could jeopardize the entire experiment. So, just like chefs do in the kitchen, chemists use tools to take exact measurements of substances. You know, um, chefs use their tools, we use our tools. Sometimes cooking could be an art, but chemistry is a science. It's not something that is creative, it's something that we must do correctly and in a precise and accurate manner. But in science, students tend to confuse the words precision and accuracy. They're very different terms, okay? You have to know the difference. So, precision is referring to how close the measurements were to one another. Accuracy is referring to how close those answers were to the true value. So, for example, we're going to look at this picture. The first one, you see these darts going straight in the middle. There is high accuracy because it's straight in the middle, right? But it's also high in precision because all the darts are close together. In the second one, the darts are not even close to the middle. So none of these darts are accurate. But just because they're not accurate doesn't mean they're not precise. So see how all the darts are close together? That means there's high precision. So there's good precision, but there's poor accuracy. Down here, there's a lack of precision. They're all far, far apart, and they're not even close to the target. So the center of the target, so it's not accurate either. When you're using the term precision and accuracy, these two terms, you need to use them in your lab reports. Every time you collect data, you tell me if the data is precise and accurate. What were you expecting to get and what did you actually get? Are they precise? Are they accurate? You tell me when you write the analysis section of your lab reports or any write up you do in science. Now, look down here. So, precision measures, let's go back to this. Precision measures how close the individual numbers agree with one another. Sometimes, right next to the values, you have something called the standard deviation. That tells you how it gives you a margin of error. So, for example, if the true value of something was 3.02, plus and minus 0.01 just tells you how how far that number could have gone. So the number could be is most likely to be 3.02, but it could probably also be 3.01 or 3.03. That's a margin of error. That's what we call standard deviation. Um, Accuracy is how close the individual measurements agree with the true value. So down there in the gray box it says if numbers are precise 3.05, 3.04, 3.04, does that mean they're always accurate? And no, it doesn't mean they're always accurate. Just because the numbers are precise doesn't mean they're always accurate. The true value could have been 6, but just because those numbers are very close doesn't mean that they're accurate. Okay? So, there's a few things that you need to know. The first thing is what is the difference between an exact number and an inexact number? And it's very important that we know this because of what we're going to learn in the future. So, um, numbers when you're measuring something, people can measure things and see things differently. So, we say that these numbers, when you're measuring, they're known as inexact. Okay, so they're inexact um, because you're measuring something that's inexact, there's going to be some uncertainties. Uncertainty means a possibility for error. a possibility for a discrepancy in numbers. So there's always uncertainty in the last digit reported for a measured quantity. Measured, anything that's measured, again, counted, measured on a scale, on a tool, it's always going to be inexact. When are things exact? It's when you're saying 5 people or 6 people or 12 eggs in a dozen. A dozen will always have 12 eggs, not 12.1 eggs, right? So 12 is an exact number. 5 people is an exact number. Okay? So know the difference between exact and inexact. So what do you think is the difference? So normally in my class, at the beginning of a chapter or section, I ask you to write a quick write. A quick write is just you using your prior knowledge. What do you already know? So what do you think is the difference between 4.0 grams and 4.000 grams? Why the heck do we even have to put a point zero? Why can't we just say 4? Why do we have to use 4.0 or 4.0000000? Why? It's annoying, but it makes sense because if you want to be very precise, you have to incorporate more decimals. So 4.0 grams, what it implies is that 4.0, so let me start over. What it implies is that 4.0 um, has an uncertainty on the last digit. So the true answer is closer to 4.0 than it is to 3.9 or 4.1. That's what it's saying. 4.000 grams is saying that the answer is most likely 4.000, and um, and it's more accurate than 3.9999 or 4.001. Um, that's what it's saying. So the more decimals that you add, um, the more accurate your number tends to be. Um, this whole idea of accuracy um, is why we use something called significant figures in chemistry. Significant figures are very common in chemistry and physics because we do a lot of things with numbers. So significant figures are critical in a lab because you don't want to create errors because you're rounding numbers like crazy. Um, so what are sig figs? They indicate the accuracy of a measurement or a calculation. So it doesn't just talk about measurements or tools, it's also talking about calculations. So whenever you make calculations, you have to round things correctly. Because if you round things like crazy, like whatever way you want, you're not going to get a very accurate answer at the very end, especially when a calculation involves multiple steps. So that is why we have something called significant figures. We don't want errors based on random ways for rounding or random ways for presenting an answer. And also, when your AP graders grade your free response section of your test, there are 7 FRQ questions on your test, and they're small. Okay, they're not big questions; they're very small. But if you don't round your answer to the correct sig figs, they will dock off points. So, like, if one question is worth 7 points, they're only going to give you 6 points if you get it right, just because you didn't round to the correct amount of sig figs. So, for example, down here, if the answer was 1 milliliter, if you put 1 milliliter as your answer, but the answer was actually 1.0 milliliters, they might consider that to be wrong because you didn't round to the correct number of sig figs. Okay, so 1.0 means that the number is closer to 1.0. 1 milliliter might mean that, it could be 0.6. 0.6 rounds to 1, right? 0.6 rounds to 1, but 0.6 is not even close to 1.0. It's like almost half of that. So that is why it's important to add more decimal places to make your answer more accurate, or to round answers to the correct number of sig figs. Now, how do you determine the number of sig figs? The most important rule is that all numbers that are not 0 are always significant. They're always important. So 1, 3, 9, 7, 8, all significant. Zeros that are sandwiched in between non-zero digits are always significant. For example, 1005, there are zeros that are sandwiched in between 1 and 5, which are non-zeros. So because of that, we say that there are four significant figures. All four of those numbers are very important. Now, number two, zeros at the beginning of a number are never significant. So anytime you have a decimal and there's zeros in the front, those are never significant. So for example, 0.005, those first three zeros, not important. So that means we only have one significant figure. Three, zeros at the end of a number are significant only and only if there is a decimal. For example, 3.0. Because that zero's at the end and there's a decimal, we say that it's significant. So there's two significant figures there. But 30 doesn't have a decimal. So even though it's at the end, it's not significant because there's no decimal. So there's only one significant figure there. See the difference? There's a zero at the end. Okay, that's cool. And there's a decimal. That gives that tells you that both of those numbers are very important. 30 has one significant figure. That last zero is very uncertain. Um, what about numbers in scientific notation? So how do you know if it's, let's say, 1.03 times 10 to the 4 power? Is it 3 sig figs? Or do you include the 4 here? So it's 7 sig figs. And the answer is you only look at the front, okay? You only look at the front. So the the correct answer here would be 3 sig figs, okay? Because if you expand this to 10,300, these last two zeros don't count. So these three would count. So it'd still be 3 sig figs, okay? So scientific notation, make sure you know how to um, how to do scientific notation, how to convert into scientific notation. So the way you do this is there's going to be a number that's not zero in the front, and then you add a decimal. So for example, 10,000 here, you start at the very end, right? Because that's where the imaginary decimal is. Then you're going to move back 1, 2, 3, 4 until you have a decimal in the front of the non-zero. So you're going to put 1 times 10 to the 4 power because that's the amount of times that you move the decimal. So times 10 tells you the number of times you move the decimal. And rule number 3 says if the number is larger than 1, then the exponent's positive. See, 10,000 is bigger than 1, so this needs to be positive. Also notice that this number only has one sig fig, so your answer should have one sig fig. Here, there's 5 sig figs, so there better be 5 sig figs in this exponential form too. 1 sig fig, 1 sig fig, 1 sig fig, 1 sig fig, 3 sig figs, 3 sig figs, 1 sig fig, 1 sig fig, 2 sig figs, 2 sig figs, 1 sig fig, 1 sig fig, because this is equal to 1. The 0 doesn't count because there's no decimal, so it's just 1. Okay, so here, for example, 2 sig figs, 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 2 sig figs. Okay, I think you get the idea. Every time you move the decimal to the right, it's going to be negative. Every time you move the decimal to the left, it's going to be positive. That's another way to remember it. So you move the decimal to the right by 19 times. So it's 1.6 times 10 to the negative 19. Or you could just remember this original number is less than 1, so it's going to be negative. That's the way I remember it, but everybody remembers it differently. Okay, so go ahead and listen to the second part of the podcast because my 15 minutes are up.